So this is again a short chapter, but to look at adaptation strategies against waterborne diseases, we again have to understand climate change and waterborne diseases in terms of environmental effects, pathogen fate, and microbial risks. So you have to know the risks to have adaptation strategies to mitigate those risks, right? That's the main goal. And we already talked about climate change manifest as water temperature increases, extended seasons for agriculture and leisure activities, precipitation increases, extreme events, and droughts, so floods and droughts. Replication of marine bacteria, so effects can be manifest as replication of marine bacteria, sometimes die-off of enteric pathogens like norovirus and campylobacter. Water purification at the treatment plant can be more efficient when water temperature increases because it's easier to perform certain processes to remove pathogens, bacteria, reduce the loading, biological oxygen demand, and so on. Organic matter and nutrients dissolve better when the water temperatures increase. There are others under extended seasons, altered demand on water treatment plants, shortened winter season with lower snow cover and reduced flooding due to snow melt. The precipitation increases can lead to runoff, sediments, organic matter, nutrients. Peak concentrations of pathogens in the surface waters are changed. Flooding of wells and water treatment plants, stormwater runoff and combined sewage overflow. Groundwater contamination with fecal pathogens like E. coli and so on. And of course, drought brings changes in water sources. People go looking for water and use sources they wouldn't use otherwise, and concentration of pathogens can get affected seriously during the droughts as well, with consequences in bacterial blooms, lower concentrations of pathogens in some places, elimination of pathogens in other cases, challenges for water treatment being less efficient. Opportunities for exposure are changed when you have extended seasons through contamination of irrigation water, for example. Reduced stress on water treatment plants, water treatment at risk, and under drought. I won't read all of these, you can go through them. Drought, for example, can reduce the treatment options, and changes for water treatment becomes less efficient as well. And microbial risk may increase or decrease depending on the effects and the consequences based on which depending on which climate change impact you're looking at. Okay, so this range of climate change impacts or manifestations, effects and consequences can tell you the risk and tell you how to reduce those risks, knowing what the effects are. Okay, that's the adaptation strategy. So look at the example of impact of droughts, for example. Infrastructure, health, sanitation, and available resources. So drought can obviously create water shortage. It can impact livelihoods, impact crop production, livestock and fisheries as well. Can increase food prices, so create nutritional issues and starvation and so on, and cause migration, forced displacement of people. All can lead to indirect health effects. So there is baseline public health and capacity for resilience that has to be monitored. So this relates again to socioeconomic vulnerabilities and physical vulnerabilities, right? For example, migration can affect the young and the old. They will not be moved, and the women may be left behind with the children and the old. Men may move seeking labor or income and so on and so forth, which exposes them to other sets of health issues. So the impacts that affect baseline public health and capacity for resilience include nutrition-related effects, mental health effects that we talked about, vector-borne diseases, airborne and dust-related diseases like meningitis, water-related diseases, of course, and other injuries, migration-related health issues, wildfires, healthcare system and infrastructure impacts, etc., leading in total to increased morbidity and mortality. So when we talk about planetary health, these are the socioeconomic, social governance policy issues along with environmental issues that we have to consider. Okay, so more specifically about adaptation and mitigation of health risks. This is an example from one of the pages that, for example, screenshots of the pages of climate scenarios of the climate change modules for quantitative microbial risk assessment tool. This is a specific tool designed for quantifying microbial risks. So it's giving users multiple options. So current climate conditions, daily average temperatures, minimum and maximum, air, water, and the days, precipitation, annual precipitation, average precipitation, heavy rainfall, number of heavy rainfall days per quarter of the year, future climate conditions, so preset versus custom choices users can make, temperature change, annual precipitation change, times of more heavy rainfall days, and shuffle heavy rainfall days. So you can change the seasonality. For example, monsoon rainfall over India, there is a decrease in the rainfall which may be recovering now related to various processes of pollution, land warming versus ocean warming, and so on. But whatever little rain is falling as very heavy rainfall events. Once the monsoon onset happens and the withdrawal happens, you have the length of the rainy season. How the rainfall is distributed within the season matters a lot for how it affects water resources, irrigation, agriculture, crop damage, floods, droughts, and so on and so forth. So this kind of tool allows you to use these informations to map daily average temperatures in a year and the water temperatures, either inland water bodies or coastal waters, depends, could be even river waters and so on, depending on what the purpose of the study is. Could be looking for contamination of fish or contamination of water, for example. They allow you to make what-if scenarios. So what is, let's say you have a seasonal forecast for the monsoon, and you can use this tool to get ready for the season in terms of managing microbial risk for the season, and also can be done at various time scales, at the seasonal outlook time scale, at what is called the extended range time scale of weeks 2 to 4, and at the weather time scales of day 1 to 10. Okay, so that's how risk can be mitigated. This is showing also the same thing here. What is the difference? This is just 2 panels. I didn't pay much attention, but seems like almost the same thing. Current climate conditions, future climate conditions, shuffle heavy rainfalls, and so on and so forth. Let's hope I didn't repeat it. So 4.6 is screenshots of the pages of the infection risk from cryptosporidium exposure from bathing water from the climate change modules of quantitative microbial risk assessment tool. Okay, so quantitative microbial risk assessment tool is telling users specifically about infection risk from cryptosporidium exposure from bathing water from climate change modules. Okay, so here, you're looking at bathing water infection risk per person per event, so cryptosporidium, current climate, and climate change. So it's the mean, and this is 95 percentile interval. So this is the climate change, and that's the current climate. Okay, relative infection risk, future and current climate conditions, densities versus relative infection risk, and you can see you can project it into all sorts of details. Okay, so these are the tools that are interactive. They are based on data and future projections of climate. They can be done also for predictions at short time scales, what are now typically called S2S time scales, sub-seasonal to seasonal time scales, where seasonal outlooks, extended range, and weather time scales can be combined to get ready the system, get it set, and get it going to deal with risks with very region-specific information. Okay, so here is an example, for example, of cryptosporidium cases in two groups of health authorities in northwest England during 1990 to 2005. And surprisingly, you can see that the health authorities themselves, with spring break, and health authorities without spring break, the cryptosporidium cases, you can see the big difference in terms of exposure to the population, that is because of spring peak and spring break. I completely screwed that up. Cancel that. Health authorities with spring peak and health authorities without spring peak. So two groups of health authorities exposed to cryptosporidium, and you can see that the cases are actually quite different. There is hardly any big peak in the case where health authorities are not subject to spring peak, whereas when they are, the cryptosporidium cases jump quite substantially. So obviously it's very easy to mitigate this kind of microbial risk with tools like this. Okay, so this is a very quick run through the adaptation strategies for waterborne diseases, but there are numerous examples. I have one chapter on S2S predictions for health in my course, another course on my YouTube channel that you can look up, where we look at examples that are forecasts made for not just waterborne diseases but also vector-borne diseases and vectors themselves, like mosquito populations, malaria outcomes, Rift Valley fever, dengue, cholera, and you can also do it for other diarrheal diseases that include typhoid, salmonellosis, campylobacteriosis, giardia, and so on and so forth. The more data you have, the more Goldilocks zones you can identify as to the temperature range, salinity range, precipitation regimes in which these diarrheal diseases or other diseases like meningitis, Kawasaki, whatever, occur, and then you can mitigate the risk. So early warning systems are a major tool in adaptation strategies to dealing with risk of waterborne diseases. Of course, works for other airborne diseases as well, but since we are specifically talking about waterborne diseases here, data, that's what it comes down to, finding the relations between environmental parameters and health outcomes. Sometimes that can be done without knowing the details of exposure pathways and so on. You can just simply find the empirical habitat relations, and when the climate predictions or climate change projections tell you those habitat parameters are going to favor increased probability of those waterborne diseases, then warnings can be issued, risks can be mitigated, and there are good examples of successful applications of such early warning systems in various regions of the world. Okay.